Hi there. So the next topic we're going to move on to is the Heisenberg's uncertainty principle. And here we have Heisenberg, Werner Heisenberg on the right, and here we have a statement of the Heisenberg uncertainty principle. So it's impossible to know simultaneously both the position and the momentum of a particle with certainty. Now this is usually written as delta x, which is the uncertainty in the position, and again we're talking about the x direction, multiplied by delta p sub x, which should be the uncertainty in the x direction, uncertainty momentum in the x direction. And the formal definition is that that's greater than or equal to h over 4 pi, or if you want to use h bar, it's h bar over 2, where we know that h bar is defined as h divided by 2 pi. Now this principle is a fundamental law of nature, and it's you can trace it back to what we've been talking about the wave particle duality of light and particles in motion. One way to think about this, it's a difficult concept, and most students and indeed teachers have problems with it. But one way of thinking about it is if you take a very simple system, so you have some particle and that's moving along, let's say our x direction. Now to observe this particle, we have to shine some light on it. Okay, so that's the way we observe its position. And so let's have a photon of light coming in here, h nu. And we know also from our previous work that you can write that as that's equal to h c over lambda. C is the speed of light, and lambda is the wavelength of that light. And we also know that that photon is going to, in the particle, the particle aspect of it is going to have a momentum, and that momentum, which we define as small p, is going to be h over lambda. So the precision that we're going to be able to measure this particle to, here along the x direction, say, and we'll call our precision delta x, is going to be proportional to the wavelength of our observing light. So if we want to decrease this, we want to make this smaller and smaller, then we're going to have to use a smaller and smaller wavelength light to observe that particle. Now as we go along and we're trying to increase the precision in which we measure this delta x here, we're going to have to go to smaller and smaller wavelengths. So as we try to reduce delta x, or increase the precision in which we measure the position of the particle as much as possible, we have to decrease lambda. But of course, when we decrease lambda, we're also increasing the momentum of the particle. So now if you treat this photon as coming in as a particle, as we go to lambda, the momentum is going to be higher. So what that's going to do, of course, is basically it's going to, if you can think of it as a particle, it's going to strike against this particle here. And of course, like any two particles colliding, where you have a large particle here coming in, then you're going to change the direction and the momentum, if you like, of this particle here. So by trying to increase the precision of our measurement, we're actually going to have a less and less precise measure of the momentum. And this really is the basis of the Heisenberg's uncertainty principle. What you call the momentum, p sub x in this case, and delta x, we call these our complementary observables. So let's write that down. So these are complementary observables. And momentum and position aren't the only complementary observables. Say some other familiar complementary observers will be the precision which you measure energy and you measure time. So again, taking our analogy up here, our simple system up here a bit further, we could write, say that, let's put a different color in, delta x is approximately equal to lambda, and similarly you could write the delta p sub x approximately equal to h over lambda. So if you then do the product, delta x times delta p sub x, what you find is that you can say delta x by delta p sub x is equal to h Planck's constant. And this in essence is the Heisenberg relationship. It's formally given as greater than or equal to h over 4 pi. But what we're saying is that the precision which we can measure position and momentum in the same direction. It's important to remember it's in the same direction. If you write delta x by delta py, say here, then this doesn't govern that product. It only governs these two products when we're talking about the same direction. But it's approximately equal to h, and this is a fundamental, if you like, a fundamental law of nature. It's got nothing to do with the measuring device we're using, how precise we can measure it. If we had what we're saying is that we had a measuring device that could measure exactly the momentum and the position, you're always limited by this value here. So let's now look at a few examples to try to ingrain this in your thinking. So we're just going to take a few examples here and see what it means for different objects. So let's talk about, we talked when we were in the de Broglie relationship, we talked about a tennis ball. So let's bring that up again. It's an object or a particle that we're all familiar with. So let's suppose now in this case we could measure the velocity of the tennis ball. So this is the precision which we measure the velocity of the tennis ball, and let's suppose that that's equal to 1.0 by 10 to the minus 6 meters seconds to minus 1. We could ask now the question, what is the precision, or what is the precision in which we could measure the position of that tennis ball, or what is delta x? And again, like the previous example, we're going to assume that the tennis ball has a mass of 57 grams. So the first thing we've got to do is work out the momentum. We know, or the uncertainty in the momentum. We know the uncertainty in velocity, and we know the mass, so we just know that the mass times that uncertainty in velocity is going to give us the uncertainty in momentum. So we can write down that delta P, that's going to be the mass times delta V, and so therefore we're going to have 57 by 10 to the minus 3, and again we're converting everything to SI units, kilograms, and the velocity is already given in meters per second, so it's 10 to the minus 6, and that's meters seconds minus 1. Now we write down the Heisenberg uncertainty relationship, so that says delta P times delta X. And now it says greater than or equal to, so the minimum uncertainty is going to be h over 4 pi. So that's from the equation which is written up here. So if we go back down here now, we can rearrange that equation because we're looking for delta x, remember, so delta x is going to be equal to h over 4 pi, and that's going to be multiplied by delta p. So that should be delta p there. So you can plug in then the values into that, and if you do that you get 6.626 by 10 to the minus 34. That's Planck's constant. and it's in joules second, and you divide that by 4 times pi, and it's 57 by 10 to the minus 3, and that's kilograms, and that's all then divided by the uncertainty in the velocity, which is 1.0 by 10 to the minus 6, and that's meters seconds minus 1. And if you plug these values in, you should get a value of 9.25 by 10 to the minus 28 meters. So what you can see here is this value is incredibly small for the tennis ball. So what it means is there is an uncertainty in the position, but it's so small that there is no way we're ever going to be able to measure this for the tennis ball. So like we had in the previous occasion when we measured the wavelength of the moving tennis ball, in this case here again it has no effect on our observation. But let's now move on to a much smaller object like an electron. So you can ask the same question again. So what is now for an electron, and we'll assume same velocity, so the same velocity as our tennis ball up there. So again, if you plug our values into our equation, so we get delta x now is going to be its Planck's constant again, 6.626 by 10 to the minus 34 joules second. Again, it's going to be 4 times pi, and now we're going to have to put in the mass of the electron, 9.11 by 10 to the minus 31, that's kilograms. And the velocity we said is the same as we have the tennis ball, so that's 1.0 by 10 to the minus 6, and that's meters seconds minus 1. And when you work that out, you should come with a value of 58 meters. So we can see that for the electron, is 58 meters is huge. So in essence, we really have no idea, or can have no idea of where the actual electron is. So this is the big difference, if you like, between looking at a classical view of particle movement and the quantum mechanical view. Classical view says we can measure the momentum and the position exactly, so therefore at any time in the future we can predict the position of that particle. So we can, if you like, work out a trajectory for that particle, a bit like we can work out the trajectories of the planets as they circle the sun. But for small, tiny objects like electrons, and this also will apply to other objects like protons and neutrons, we can't do this. In other words, we can't trace out trajectories for the electrons, say, circling around the nuclei. And all we can do, as we show when we go on to move about onto the Schrödinger equation, is we can work out what are called wave functions, and all we can do, and all we're limited to do, is work out the probabilities of where the electrons will be.